Overview. This video demonstrates Scenario 2, Chlorinated Solvent Contaminant Transport. We can click the SCN02 item for detailed information about this problem. This is an advanced scenario. If you're using this function for the first time, we recommend watching the previous video Scenario 1 to get familiar with the basic operations. The simulation area represents a horizontal cross-section within a rectangular area at the desired simulation depth. Users can define the field boundary by map and freely adjust the length and width dimensions, and modify the mesh density. The default setting assumes a single hydrogeological material, defined by porosity, hydraulic conductivity, and density. Users can input constant water head boundaries for upstream, left side, and downstream, right side, or use site-specific water elevation data for configuration. The simulated pollutants are chlorinated solvents, including trichloroethylene, TCE, dichloroethylene, DCE, and vinyl chloride, VC. The model simulates dissolution, adsorption/desorption, and other geochemical reactions. Users can adjust the contaminant distribution at the boundary and modify the initial concentrations. After running the simulation, the model produces results indicating changes in aquifer conditions, saturated and unsaturated zones, and groundwater flow dynamics. With the coupled chemical transport module, the simulation can provide insights into how contamination plumes evolve over time due to groundwater flow, helping users assess potential impact zones. Next, select Load to open the Scenario 2 template. Then we will see the simulation interface for setting up Scenario 2. From here, we can begin customizing the parameters as needed. First, set up the geometry. In this example, we are using a map, which is spatially accurate and based on real-world coordinates, to set up the simulation area. We can click Map and see the map interface. On the right side, the main menu includes Coordinate Input, Map Settings, Toolbox, and Boundary Configuration. From the toolbox, we can also save the maps. Next, we define the simulation boundary. You can zoom in and out using the mouse scroll wheel to inspect details or view the entire structure. To move the center location, double-click the left mouse button, which will display a yellow rectangle highlighting the selected area. Right-click to move the entire boundary, and also to open a submenu where you can set multiple sources. Here, a rectangular area of 50 meters wide and 100 meters long has been set, aligned with a 0-degree angle. Right-click the mouse, and we can see a green arrow representing the domain's center position. Click Set Boundary and show the highlighted, red-filled rectangle over the map. The map automatically divides the area into directional zones, upstream, downstream. Next, Set Source places red markers labeled Source 1 and Source 2. Similarly, by selecting Set View, a yellow marker labeled View represents the monitoring or observation point. We can easily reposition the source and view points by right-clicking on them and moving the mouse to the new location. Finally, close this map interface, and it will auto-save. The geometry setting is completed. Then, configure the mesh. Go to the mesh settings. Select the moderate option from the list. Then, set the mesh density to 0.3. Define the parameters. Begin by setting the material properties for the hydrogeological layer. Choose sand as the material, with a porosity of 0.35, a hydraulic conductivity of 0.002 meters per second, and a density of 1.895 grams per cubic centimeter. These parameters control how water flows through the subsurface environment. First, we set the water table elevation at the upstream side to 3 meters and the downstream side to 1 meter. This creates a hydraulic gradient that drives groundwater flow from left to right. Next, we specify the contaminant concentration for both sources. Here, we assume both Source 1 and Source 2 contain trichloroethylene, TCE, with a concentration of 0.5 mg per liter and 0.3 mg per liter, respectively. After setting the environmental conditions, we define the total simulation duration. In this case, the model will simulate the contaminant transport over 150 days. Select the output method. Now, click Execute and wait for the model to run. First, we'll see the geometry results based on the view window we set earlier. Next, go to Animation and click Play to visualize how velocity and pressure head, TCE concentration change over time. In the plane view, arrows show the flow direction, while color gradients represent water elevation and concentration for TCE. Then, under the View section, we can check the observation point's velocity, pressure, and TCE concentration results. Finally, visualize and interpret the results in the Site Management GUI. Clicking on the Site Conceptual Model Information GUI reveals the main layout, including the render view, spreadsheet, and resource sections. On the left, we have the resource browser. This section allows us to toggle between different visualization datasets, including pressure, velocity, and TCE concentration. Click checkboxes to toggle different data layers. Emphasize that TCE is currently selected. In the center, we see the render view of the simulation domain. The color map represents TCE concentrations in the subsurface, with red areas showing the highest concentration near the source. At the bottom, we see the simulation data in tabular format. Each row corresponds to a spatial node, displaying values like coordinates, x, y, z, velocity components, pressure, and TCE concentration. The spreadsheet helps identify exact node IDs and values valid for validation and post-processing. We can customize the display settings to enhance the clarity and interpretability of simulation results. The scalar range is automatically calculated by default, but we can manually input a range for better contrast. We can also change the color scheme. Here it's set to rainbow. One key feature is the display mode, which defines how the mesh or surface appears on screen. We can choose display mode, such as surface, which provides a clean contour look. Surface with edges shows element boundaries, functional for mesh inspection. Wireframe displays only the mesh grid lines, which is excellent for structure checking. Thank you for your watching.